Welcome back to the first law of thermodynamics in physical chemistry. My name is Kevin Tokoph. Make sure to like the video, subscribe to the channel for future videos and notifications. In this video, we're going to go over an introductory topic to thermodynamics in physical chemistry, and that's the concept of work. Now, if you took any kind of lower division physics course, which is usually a prerequisite for this class, you probably would have talked about the classical definition of work, and that's that work is equal to the integral of force times dx. Now, what this basically says is if you have any object, okay, and you move this object over a distance, x1 to x2, using a force, then you take the force, could be a function of x, multiply by dx, integrate it, and that's the work done. Okay, if the force was constant over that period of movement, then you just multiply the force times x times delta x, basically. Okay, and that's the work done. Now, in the context of physical chemistry, we're normally not dealing with moving an object just simply in one direction. Okay, so an example in classical physics that you would have seen in your lower division physics is if you just have a can on a table and you want to move the can from one point on the table to the other, you simply take your hand, right, and you just push it, right? You push the can from x1 to x2, right? However, when we're dealing with chemistry, we're ordinarily dealing with things like gases, okay? And you can't just take a gas molecule and push it along a single direction in the x direction. You can't just push it from one point to another because the gas molecule is moving in all directions, okay? And there's not just one gas molecule, there's going to be maybe several moles of gas molecules. And so it's a lot harder to deal with that definition of work that we just looked at. Let's take a look at the cylinder. So the initial conditions of the cylinder are defined by only the markings that are done in white. Those are the constraints of the cylinder. Now, if you look at the cylinder at any point in time, the cylinder's side here, the circular part, has an area, and this is just a circle essentially. The circle has a radius r, and so if you wanted to find the area of the circle, then the area is just given by pi times the radius squared. Okay. Now, if you go along the x-axis here at any point, so here, there, even out here, whatever, notice that the area doesn't change with where you are on the x-axis. In other words, the rate of change of A with respect to x is 0, meaning that area is a constant. Okay, so over this whole cylinder, area is a constant. Okay, now suppose this part of the piston right here, suppose this is a piston right here, and I can move that sort of side of the piston left and right. Well, suppose I move it from where it is right here at x1 out to here at position x2. Well, we sort of have an intuition. If this initial condition of the cylinder is filled with the purple gas, if I move this piston out and increase the volume from x1 to x2, then the gas is going to fill the rest of this container. Overall, the gas is going to have a lower density because the volume of the cylinder would have gone up, but the gas is going to essentially be homogenized as it moves from this area right here to fill all of this area, which includes from x1 to x2. Okay. Now, what I've done here, essentially, is I've changed the volume of the cylinder. Why? Because I've essentially extended this piston out from x1 to x2. Okay? Now, if we look at the generic volume of a cylinder, or really any object, we can take an area, okay, multiplied by x, and we get the volume. Okay? So in other words, if I were to take for this white component, the white component right here from here to there, let's call that x prime, then the volume of the cylinder at that point would be the area, which is pi r squared, times x prime. That's just the area of this white part. Now suppose between x1 and x2 right here, this change in x right here, I'm just going to pick an infinitesimally small rectangle right here, and its width is going to be dx. Okay? Now, if I take this same formula right here and just apply it using a differential x component, then I find that the area times dx is actually dv. Okay, so in other words, if I were to look at this little rectangle right here, and technically the rectangle it's basically circular, okay, it's sort of like a disc, in other words, you can think of it that way, then dx times the area is dv. Okay, it's actually a volume because it's not just a rectangle. It's essentially just a cylinder like this of infinitesimal width, okay, dx. And that's going to become important because if any time I multiply area times dx, I get dv. Okay, so why is that useful? Well, if I come back over here, what I'm going to do is within this integral of force times dx, I'm going to multiply by what's referred to in physics and math in slang term as a fancy 1, a over a. So you take any number and divide by that number, or any variable and divide by the variable, it's just 1, right? I could take 3,355 alpha squared beta t, whatever, and if I divide by 33,055 alpha squared beta t, it doesn't matter what these variables are, right? It's the same thing, that's just 1. Right, it doesn't matter what these are, this is 1. So, in other words, by throwing an a over a into this integral, I didn't actually change the value of the integral, okay, because a over a is just 1. But what happens is I can sort of rearrange where the a and the 1 over a are, and I can put the 1 over a, notice, over the f, so force divided by area. Now, if you're not familiar with force divided by area, go back and watch the previous video, but force over area is just a pressure, okay? So this quantity right here, this is just a pressure, okay? And then a times dx, we just said that was dv. In other words, if I want to find work due to a change in volume and due to a pressure, then the work is equal to the integral of P times dV. And this is the definition of work in a thermodynamic system due to a change in volume due to a gas. So we would say a compression or an expansion of a gas. Okay, now sometimes in the context of engineering courses, you may see the work or PV work as having a positive value. Normally in chemistry, this has a negative value, and we're going to explain why that is by looking at the following set of examples, by looking at the system and the surroundings. So I'm going to consider this system right here, everything contained in this white circle. We're to assume there's a gas inside here. The surroundings is everything outside of the circle or outside of the system, okay? Now, the way we define whether a state function or a path function is positive or negative is whether or not energy is added to the system or taken away. Okay, so let's assume for a second that work is done by the system. Okay, if the system does work on the surroundings, well, work is just energy, right? It's a form of energy. Okay, so if the system is doing work on the surroundings, that means energy is being transferred to the surroundings, so the system is losing energy. And because everything is with respect to the system, if the system is losing energy, then we say the work is negative or work is less than 0. An example of that would be if we have a small volume right here with a gas in it, and we do what's called an expansion of the gas. In other words, the volume is increasing, or delta V is greater than 0. This is an expansion of the gas, and because the gas is losing energy because the system is doing work on the surroundings, the work here is negative. Okay? Now let's look at the opposite case. Let's suppose the surroundings does work on the system. In other words, that would be like a compression, as shown right here. So we start with a large volume, and there's a gas inside there. Suppose we compress it. In other words, we shrink the container, so now the gas has a higher density in the container. Well, the volume's dropping, that's a compression, and because the system is gaining energy because the surroundings are doing work on the system by doing the compression, we would say that the work is going to have a positive value because the system is gaining energy. This is going to be an important concept when we look at other functions like heat, enthalpy, entropy, Gibbs free energy, Helmholtz energy, and so forth. Anytime the energy is added to the system, we say that that energy has a positive value. If the system loses energy, then it has a negative value. Okay? Now, this is sort of what we want to look at. When work is done to the system, we want the work to have a positive value. So the question is, how do we get the work to have a positive value if our definition in general is that PV work is equal to the integral of P of the pressure, it's actually going to be the external pressure, times dV. Well, the answer is we throw in this negative sign here, okay? And let's explain why that is. And this is just a convention in physical chemistry. So let's suppose that just for a moment I have a constant external pressure, okay? So if I have a constant external pressure, that means I can pull that pressure outside the integral, in which case I'm just integrating dV from V1 to V2, okay? And since I'm integrating from V1 to V2 of dV, just a differential element, that means that my expression for PV work just becomes negative external pressure times delta V, okay, because pressure is constant. Now, let's say we're looking at the case where work is being done to the system and work has a positive value. We'll look here at the example. When we do something like this, which is a compression of the gas, we start with a larger volume, compress the container to a smaller volume. In other words, this right here is V2, this is V1. So if we take delta V, which is always going to be V2 minus V1. Notice that V2 is smaller and we're subtracting a larger number because volume 1 is larger. That implies that delta V is going to be a negative value. That's what we indicated right here, right? So when I do this, I'm going to get a negative times the external pressure times a volume that's negative, or a change in volume that's negative. So when I do this, okay, the pressure is going to be positive times a negative number. That means overall, this is going to be greater than 0. Okay, so that's why we throw this negative sign in there that you might not expect. Okay, it's to force whenever we're doing a compression, meaning we're doing work on the system. Okay, we want the work to be positive. Okay, and you can actually show that if you were doing an expansion of the gas, meaning delta V is greater than 0, hopefully you can see that dV, or delta V, would be positive, and the work would be negative, because the system would be losing energy because the gas is expanding. Okay, so hopefully that makes a little bit of sense. Okay, now one thing that's very important here is, remember when you looked at the classic definition of work from physics, you said that it's equal to integral of force dx. Okay, well, what if you're applying a force on something, but there's no movement? The example that's always given is if you have a concrete wall, okay, you go up to it, it doesn't matter how hard you push on it, it doesn't move, right? You're applying a force, but are you doing any work? Well, you're not doing any work because in that case, dx is 0. Also, delta x is 0 because the wall is not moving, right? So if dx is 0, then this integral is 0 and the work is 0. And that's in the classical case. But there's also an analog in the thermodynamic case. In some cases, and we'll introduce this in a few videos, you can have a process, a thermodynamic process with a gas that's something called isochoric. Okay, this is probably a term you haven't heard yet. What does isochoric mean? Isochoric means that you have a process where the change in volume is 0. Okay, meaning that V1, the initial volume, is equal to V2. The volume doesn't change. Okay, the container where the gas is isn't changing volume. Okay, so if we were to look at the PV definition of work here as being the negative integral of P external dV, we can even put from V1 to V2. Well, if this is an isochoric process, delta V is 0, which also implies that dV is 0, right? In which case this dV goes to 0, the whole integral goes to 0, and the work done due to an isochoric process is 0. Okay? This is going to be a really important sort of identity that you'll need to know for future problems that can get pretty lengthy, that if you have any isochoric process, the PV work, which is generally all you're dealing with, is 0. Okay, and that's because there's no movement. If we have a situation where the container isn't changing volumes, then the gas isn't changing volumes, and so there's no work done because the container is not being moved, compressed, or expanded. Okay? So hopefully that gives you a little bit of intuition on work. In the next video, we're going to go into a little bit of heat and the definition of heat capacity. See you in the next video.